keeping track of time. So if you can let me know when to start, that'd be great.
Yeah. No, you're actually right on time. 1:21 was what I had. So yeah.
Oh, okay, cool. So should we get into it then?
Let's do it.
Okay. All right. So we have a slide deck prepared basically to introduce you guys to some of the fundamental ideas and concepts in quantum computing. Before I start, just want to emphasize that this is a very high level introduction, and I won't try to go into much depth, but if there's anything that doesn't make sense to you in this first lecture, don't worry. We're going to go into all of these topics in a lot more depth in this semester and next semester as well, for those of you who stay in the course. So hopefully everything I'm saying to you today will make a ton of sense by the end of this semester. And then next semester, we'll get to explore some of the more advanced applications and ideas. All right, so to start off, let's begin by discussing what exactly a quantum computer is. A lot of you might have heard about this from kind of like news outlets or maybe in some sort of hyped context. I will say there's a kind of a lot of misinformation out there about what a quantum computer actually is. So one of the goals of this class is to kind of debunk some of the myths about what a quantum computer is and what it's useful for. One of the really cool things about being in quantum computing in this kind of early of a stage of the development of the technology is that actually a lot of questions about what quantum computers are and what they're good for haven't fully been resolved yet. So we're really at the like cutting edge of this technology. And there's still a lot of really important open questions left in the field that researchers like Amir and I are currently trying to work on. And for those of you interested in continuing in the field, you also can work towards and hopefully help us try to answer. All right, so at a high level, a quantum computer uses properties of quantum mechanics to solve problems that classical computers cannot. And through the course of this class, we will learn exactly what these specific properties are. For those of you who aren't familiar, quantum mechanics, which also is sometimes known as quantum physics, describes how really small objects behave. And when I say really small objects, I mean things like atoms, electrons that you hopefully have already maybe seen or heard of in like a chemistry type context. These are really the kind of like the smallest units we know of, dating back to like kind of the ancient Greek notion of atom being kind of like the smallest fundamental element. And of course, there are more advanced theories of physics, which have theories for what lies below those, but those we think of as kind of fundamental particles, really small entities. So small, of course, that we can't see them with our eyes. We have some really fancy, maybe devices, which we can use to image electrons and things like that. But yeah, just think of these as really small entities and quantum mechanics as the theory that describes the properties of these really small entities. And so one thing that's really interesting, and kind of the interest from quantum mechanics, comes from the fact that physics have discovered that these really small objects don't actually obey the laws of classical physics. So for those of you who might have taken a class in, say, classical mechanics or taken an introductory physics course, you've probably learned about the standard Newtonian equations like F equals ma and those sorts of things, which allow us to predict how big things will move. So for example, you could predict the trajectory of a soccer ball when you kick it, all those sorts of things. It turns out, however, that all of these laws that you learn about in a classical mechanics setting don't actually apply at the really small scale. And so for that, we need a whole new type of physics, and that physics is quantum mechanics. So just to give you an idea of some things that are different in the quantum world, properties that quantum phenomena exhibit that big, large classical objects do not, are things like superposition. So for example, in the quantum world, you have objects that can simultaneously be in multiple states. So the kind of common popular science example is Schrodinger's cat, where you have a cat that's both dead and alive. You can imagine someone being both upset and happy. Those are two different possible states. In terms of position, you could imagine something simultaneously being in one place and another, and so forth. Another example is this notion of tunneling. So it turns out that in the quantum world, objects can actually pass through physical barriers. So we know that in the classical world, right, unless you're in Harry Potter, if you run at a wall, you're not going to really be able to pass through it. In the quantum world, however, it turns out that atoms, small particles, they can actually physically, if they're moving fast enough, or have certain properties, tunnel through literal physical barriers. And then finally, just a final example is teleportation. So this concept of teleportation you frequently see in like science fiction movies, right? Where someone's, say, in the US, and then they get into this really wild, fancy machine, and then suddenly they've been teleported, say, to the other side of the world, maybe to China or something like that. It turns out that in the quantum world, you can actually teleport information over large distances, just like you see in those science fiction movies. So all of these are really strange, but cool and awesome properties that we really only see at the quantum level. And in quantum computing, we'll see that we leverage a lot of these properties. So going a bit further into that, there's actually three kind of main properties of quantum mechanics that are really important to quantum computing. The first one is the notion of superposition that we just talked about. The second is the notion of interference. And to give you some insight at a high level of what I mean when I say interference, you can think about what happens if, for example, you were to drop two stones into like water. The rippling pattern of those stones would kind of propagate towards each other, and they would interfere in a way such that you get constructive and destructive interference. And it turns out that quantum particles, even though they're particles, they also have wave-like behavior in which you can like constructively and destructively interfere certain aspects of the quantum particles or objects. And the third final property is entanglement, which really is kind of cool, crazy quantum phenomena in which you can kind of like establish quantum correlations between particles. So when I was first learning about quantum mechanics, the example that was given to me to explain this notion of entanglement is like, say you have a pair of gloves, one goes on your left hand, one goes on your right hand. You put those two gloves into boxes, you take them to other sides of the universe. What entanglement tells us is that if a person on one side of the universe opens the box and sees that they have the left-hand glove, it must be true that the other person on the other side of the universe instantaneously knows that they have a right-handed glove. I guess, Amir, do you have any other way you want to, at a high level, give a notion of what entanglement is?
Yeah, so I mean, Fran, that was a great example. Now, what's really fascinating about entanglement is that, so I mean, left and right hand gloves, that's one example, right? But let's say you have two entangled objects, you can ask like different questions from the objects and their correlations will remain the same. So, one example slide that we'll probably see, whenever we talk about entanglement in this course is, let's say like, I like cookies, like, like a waiter asked me in Cambridge, Massachusetts, and Fran in Berkeley, whether, we want like, I don't know, chocolate milkshake or vanilla milkshake. And if we're like somehow entangled, I always say chocolate, Fran will say vanilla. Like, another question could be cookies or brownies. And like, regardless of what question we're asked, if we're entangled, our answers will always be different. And this is kind of the fascinating non-classical behavior that I feel like leads to a lot of these cool applications in quantum computing. Now, again, we're going to talk about this in more detail with better examples down the road, but just to give you guys a flavor of what's ahead.
Yeah, and all of these are, I guess, just to say, these are all inherently very unintuitive concepts, which make quantum computing and quantum mechanics special relative to classical mechanics. So if you're still really unsure as to what these three properties mean, don't worry, we're going to go into a lot of depth of them over the course of the semester to hopefully build that intuition. Since these are really the three kind of key ingredients or building blocks of quantum computing. So yeah, this is just summarizing what I just said. And so kind of the goal with quantum computing is to actually harness all of these fascinating properties to make computers faster and more powerful. And speed is a kind of important thing in computing, right? The whole goal of computing is to be able to do things much faster than, say, we as humans would possibly be able to do by, say, like adding numbers. With a computer, you can much more efficiently add numbers, and in turn that enables you to like much more quickly solve harder problems that require a lot of computation. But it should be noted that quantum computers are not different from normal computers in that they just do things faster. For example, we already have examples like your laptop is inherently a lot slower than the world's fastest supercomputer. But even though the world's largest supercomputer is faster than your laptop, it's still fundamentally doing the same type of computation. It's just that it might have more chips, faster networking between chips, things like that, that are more just hardware changes that enable you to do that same type of computing just faster. In quantum computing, you have to realize we're actually not just making things faster by changing the hardware, but we're kind of fundamentally also changing the way in which we do computation. And over the course of this semester, we'll learn what that type of computation is and how it deviates from standard classical computation. And so then you might ask, well, why actually do we need a different type of computation? For all intents and purposes, you can do a lot of really cool stuff. Most things you could think of doing, you could already do with like your laptop. So why is it actually important to build quantum computers and implement a whole new type of computation? And one of the original motivations for quantum computing actually comes from an idea very linked with classical computing, which is this notion of Moore's law. So about 50 years ago, Gordon Moore, who is the co-founder of the company Intel, that builds a lot of the chips that most modern laptops and computers use, he predicted that the power we could squeeze into a computer would double every year. And so on the right, you can actually see a graph that has like actual real world data of kind of the number of transistors on your chips, where transistors correspond to the fundamental bits that you can perform computation on. And of course, the more kind of transistors you can fit onto your chip or into your computer, the more computing power you have. And you can see that that's been following a pretty exponential trend since the 1970s up till 2020s. Oh, sorry. And the way that people have been able to kind of make that exponential trend progress so far is really by engineering the transistor itself and working to make it smaller and smaller as the years progress. And so just to give you a sense of the scope, the modern transistor is around 2 nanometers in length. This is insanely small. A human hair is actually 50,000 to 100,000 nanometers thick. So the transistors that your laptop or your computer runs on are like several hundreds of thousand times smaller than even just like a strand of your hair, which is pretty wild and an incredible engineering feat. But what we found is that actually we're making transistors so small nowadays that we've reached an actual physical limit to like our ability to make them any smaller. By only being a nanometer long, transistors have basically approached the size of approach such a small scale that they actually now are hitting kind of the quantum regime, where you start to see these properties like tunneling and things that didn't apply at the larger, more classical level. And this creates all kind of problems if you're trying to build a computer. And basically, it just prevents engineers from actually being able to make transistors smaller. So what we've seen in more recent years is that computer engineers, they haven't been able to continue this exponential growth by making transistors smaller, but by being more efficient, say, in how they lay out transistors on a chip, things like that. And that's actually really harmed our ability to continue this exponential growth in building classical computers. And there is actually concern, a fear, and we're now starting to see actually that we're no longer really following this exponential growth. So our ability to continue scaling classical computers is really starting to hit a limit. And we kind of need a new way forward to continue speeding up our computers. Amir, was there anything you wanted to add? Or... So the kind of key idea between quantum computers then is, well, if, say, our classical computers, they're hitting this fundamental limit because we can't really make them any smaller. Well, why don't we actually maybe try and leverage quantum mechanics and actually create a model of computation that's based on really small bits and embrace the quantum properties that come with using these small bits, or engineer quantum systems where we can leverage these properties like entanglement, superposition, interference to implement a whole new modality of computing. The original idea for quantum computing actually came from Richard Feynman back in the 1960s when he said, he, I guess, for some context, was one of the founders of the field of, or not a founder, but he was one of the leaders in quantum mechanics. And so he was thinking a lot at the time about like simulating quantum objects. And he said, ultimately, if our goal is going to be able to simulate quantum objects, well, shouldn't we want to simulate those on actual quantum devices themselves? It doesn't really make sense to be trying to simulate quantum mechanics on classical computers. So what if we built computers that actually were quantum in themselves? And that was really the originating idea for quantum computers that then eventually developed into the field of quantum computing. So that was a bit of background, but now we want to spend a bit of time discussing the quantum revolutions. How did we get from the development of quantum mechanics to kind of the modern day state of quantum computing? So the first quantum revolution really took place in the early 1900s when scientists realized that classical mechanics didn't really apply at the microscopic level. They started realizing that something was wrong with their understanding of the universe, and that physics was fundamentally different at small scales. And on the right, you see a photo from the World Solvay Conference, in which there are some photos of potentially famous scientists you might recognize, like Albert Einstein, who, although he's really known for his contributions in relativity more generally, did in fact receive his Nobel Prize for his work on the photoelectric effect, which was one of the kind of key original experiments in and thought experiments in the development of quantum mechanics. There's a lot of other famous people in the photo, but I won't spend a lot of time boring you with the history of quantum mechanics. But kind of this revolution in the development of quantum mechanics is what we really call the first quantum revolution. And so as part of this first quantum revolution in the last 100 years, since the early 1900s, we've learned what makes up atoms and molecules, and we've also learned how light behaves and how materials behave, and kind of the interaction between them at the small scale. And through this understanding, we've been able to build devices which are able to leverage quantum physics. For example, you have lasers, GPS, MRI machines, and even our phones, which are used very common day to day, but kind of all of these devices require an understanding of physics at the micro scale, and leverage some quantum phenomena in order to do the really cool things they do. So in reality, quantum mechanics is probably integrated in your day-to-day life in ways that you don't even realize it. Now, the second quantum revolution is what we're going to call the more recent revolution in quantum, which is scientists actually leveraging the properties of quantum mechanics, and really focusing on controlling individual quantum systems to develop powerful new technologies. So kind of some examples of this include not only quantum computers, but there's been a lot of recent work on kind of the quantum internet, and even in quantum computing itself, one of the modalities by which you can build a quantum computer, for example, is by trapping ions in magnetic fields. And that requires really specific ability to control small, these microscopic objects and really manipulate and harness their quantum properties. So in this class, we're really going to focus on the aspect of the second quantum revolution that is quantum computing, but it is important to note that there's a lot more to this second quantum revolution that is going on today, and that researchers are actively working on than just quantum computing alone. Quantum computing is actually part of an even larger field called quantum information science and engineering, which studies the many different uses of quantum mechanics. And this field has grown significantly in recent years. And kind of beyond quantum computing, you have things such as quantum sensing, quantum networking, which are all just kind of ways of trying to build, say, for example, more powerful sensors, or thinking about how you can distribute quantum information, things like that. And so now we're going to discuss a bit the applications of quantum computing. And we've put here a caution work in progress sign because I guess quantum computing is still a very nascent, recent field. And for those of you who I guess like to follow the quantum computing news or media, you might have seen that even today, while there is lots of cool research and results coming out every day in quantum computing, we still don't really have large enough quantum computers to be able to run really useful algorithms and kind of test our ideas for possible algorithms that we think could work better than classical computers. So applications of quantum computing is something that people are thinking a lot about and really excited about, but we don't have a lot of demonstrations of these applications of quantum computing. It's something we're currently working towards. And I guess, Amir, I don't know, did you want to go through these applications? Should I?
Yeah, let's do it. I mean, just hop on the next slide. Let's go on the next slide. Yeah, so again, Fran, feel free to jump in whenever. But there are certain areas, certain problems that we know for a fact based on mathematics that quantum computers can offer an advantage over classical computers. So, one example is searching through a list. So normally if you're searching through a list in a classical computer and the list is unsorted, chances are you have to go one element at a time, and worst case scenario, you have to make, as many queries as the size of your list. However, with a quantum computer, you can do this quadratically faster. So instead of looking at, all the elements of the list, let's say n elements, you can only do square root of n operations and get the right answer. We'll see why down the road, but that's something fascinating about quantum computing. Quantum mechanics can guarantee you security in transmitting data based on the laws of physics, as opposed to some mathematical problem that's hard to solve. So the most common encryption protocols that are used for transmitting data between, let's say, you and your bank, or like really between any two parties, rely on the fact that factoring or some variant or similar problem is difficult for classical computers to solve. But if there's an algorithm out there, you could easily break the encryption and essentially render it useless. However, with quantum mechanics and something called quantum key distribution, again, we'll talk about those protocols down the road. You can transmit your data, and the security will be guaranteed by the laws of physics, not by the fact that, hey, there's a problem that we can't solve yet. And of course, the last item here on this list, which is very near and dear to my heart because it's my PhD research, is simulating quantum mechanical systems. Now, again, we will see why, but classical computers are really bad at simulating quantum mechanical systems. In fact, I think the largest molecule that we've been able to simulate on the supercomputer only has up to 50 electrons. So it's a small system. However, if you have a quantum computer, you can leverage the quantum properties of your quantum computer to do the mapping between the quantum system that you want to simulate and your quantum computer. And again, the fact that you have something that's quantum mechanical allows you to make these operations and these simulations much faster. Friends, anything you want to
add? No, I think that was a good high-level summary. And yeah, I guess to continue off of what Amir was saying, quantum computing, in having kind of these benefits over classical computers, we can foresee a lot of applications to a wide varieties of fields. So just to name a few fields that people are currently researching and thinking about applications of quantum computing, there's been some work in finance. Cybersecurity is really at the heart of quantum computing. One of the first, I guess, big algorithms that was to come out and made people excited about quantum computing was Shor's algorithm, which basically showed that if you had a big enough quantum computer, you could hack any almost any crypto system in use today. So that created a lot of interest in the field of quantum computing in itself, but there's also a lot of really exciting ideas for how we could use quantum computing in biology and chemistry for drug development, and really important applications. There's some work applying it to aerospace as well. And as I mentioned earlier in the lecture today, I personally am pretty interested in the intersection between quantum computing and machine learning. But a lot of these applications are still very early on, which is pretty exciting because it means there's a lot of cool potential to explore and think about how we could use quantum computers to solve a lot of the world's hardest problems. So I guess to go into a bit more depth on a few of these applications in the context of cybersecurity, as I briefly mentioned, quantum computers pose a serious risk to modern day encryption, and they threaten to break commonly used encryption methods. We could also use quantum computers to create unhackable security networks. So for example, modern public key encryption has basically been virtually unhackable by using very long key pairs, around 617 decimal digits. However, an advanced quantum computer using Shor's algorithm, which I just mentioned, could crack this in just a few hours. Now, you don't have to be afraid for right now of anyone hacking into, say, your email with a quantum computer, because right now the largest quantum computers we have are still pretty small and noisy, and they only have on the order of just over 100 qubits. To run Shor's algorithm to actually hack into a modern crypto system, you would need like a fault-tolerant quantum computer with tens of thousands or hundreds of thousands of qubits. I don't know the exact number, but it's still pretty far from where we are today on the experimental forefront of building quantum computers. But because there is this risk of quantum computers being able to hack into modern crypto systems, that's also led into the development of a whole field called post-quantum cryptography. So now there's a whole field of computer science dedicated to trying to think about how we can make our computers safe, even in a time when there are large quantum computers that could, say, run Shor's algorithm. So moving on to the context of molecular biology, in this context, we have belief that quantum computers could help with things like vaccine development. So this should be something that we're all of interest in, especially in light of, say, for example, the recent COVID-19 pandemic. For classical computers, basic calculations predicting the behavior of a medium-sized drug molecule could take a lifetime to compute accurately. So one of the big kind of open problems in biology and chemistry is this question of protein folding. And there's been a lot of recent work on the ML side in particular to try and help with this problem. Recently, there was a big breakthrough by AlphaFold, the company DeepMind, for those of you who might be interested in looking into it. And this was a really big achievement in the field of ML to try and make protein folding better, because protein folding is pretty important for drug development and all of that. But even then, there are a lot of limitations to how well the algorithm worked and is computationally very intensive. That said, we believe that quantum computers could significantly help improve the early stages of drug development by helping us do things like quantum simulation, simulating the fundamental molecules and helping us get a better understanding of things like protein folding. And overall, this would enable us to reduce the number of development cycles and shorten screening times in drug development. So that hopefully in the next pandemic, if we had quantum computers available, we could roll out a vaccine much faster. So moving on to another really important application, there's also a lot of work thinking about how quantum computers could be used to combat climate change. And again, kind of similar to the context of drug development, by being able to simulate kind of quantum phenomena, quantum simulation, we might be able to simulate kind of the more fundamental molecules and processes happening in agriculture, so that, for example, we could develop kind of new fertilizers or new agricultural processes that would enable us, say, to more efficiently grow food, helping address world hunger, while also helping combat things in the climate, or helping reduce climate impacts. Agriculture is just one example, but there's a lot of other aspects of our world in which we could think to apply quantum computers to improve things like supply chain and fuel, things like that. I guess, Amir, do you have any specific examples in mind?
Yeah, I mean, again, I think the best known or the most well-known example is of the example of simulating chemical reactions and how we can use that to possibly make the process for synthesizing ammonia a little bit more efficient. So right now there's a lot of energy costs that goes into into simulating the process on classical computers, but also just like generating ammonia. I think it's about like 1% of the world. It's like a percent of the world's total energy usage. And now if you can come up with a more efficient process for generating ammonia, then all of a sudden you can save a lot in terms of energy usage. And again, grow better food, hopefully, or in general, push the capabilities that we have when it comes to farming. And that's the most notable example, but of course there are a lot of other examples, all around.
Cool. So as you can see, there's a lot of really cool ideas for applications of quantum computers, but as I mentioned earlier, right, the main kind of barrier in reaching all of these really awesome applications is the continued development of the actual quantum computers themselves. So building larger, less noisy quantum devices on which we can begin to actually test out some of these ideas for our applications. And there's a lot of estimates for when we will actually be able to have these kind of large, less noisy quantum computers that are good enough to run some of these algorithms that we have at a large enough scale where they can make an impact on important problems. On the slide here, we have an estimate of 5 to 10 years. I think this is probably a bit more of a hopeful estimate. There's still a lot of work to come, but we've already seen some demonstrations. For example, Google had what they called their quantum supremacy result, in which they were able to outperform the world's largest supercomputer for a specific task, even using a small, noisy quantum device. So it's hard to say, but hopefully soon we'll have big enough, good enough quantum computers where we can really start to apply them to these important problems. And with that, we just wanted to also discuss a bit what the current quantum ecosystem looks like. And by this, I mean the application and work and research of quantum computers in all different domains, spanning from university to government to industry. So with regards to companies that currently are putting a lot of investment and focus on quantum computing, there's like a very wide variety of them across all different kinds of fields. We'll go through a few examples, but there's tons more than we'll have time to go into. In one example is ExxonMobil, which is basically using these ideas of quantum simulation to try and develop better means of generating fuel and more efficient, I guess, fuel processes. There's a lot of automotive industries that are really interested in using quantum computing to improve their supply chain. BMW, namely, is hosting a conference on quantum computing for automotive challenges. But yeah, a lot of big car companies are currently investing in quantum computing. In finance, there's a lot of interest in using quantum computing for optimization problems. And I guess in finance, being able to make speedy transactions is kind of the utmost important. So if you have inherently faster computers, that gives you a bit of an advantage in the finance space. So companies like Goldman Sachs are looking to incorporate quantum computing into their financial prediction pipelines. And then in the healthcare space, there's of course a lot of interest in quantum computers for drug development. One recent example is the Cleveland Clinic has partnered with IBM Quantum to see how they can leverage quantum computing and artificial intelligence for kind of healthcare and life science research. But this is just, again, one example out of the many healthcare companies looking into quantum computing. In terms of more so on the academic research side, there are tons of universities that have established quantum computing and more general quantum research programs. On the slide, we have just a few, but there's 100 more out there. That being said, quantum computing is still a fairly new, recent, exciting technology. So there's still a lot of universities which have yet to create quantum programs, but a lot of them do, and it's a really exciting time to get into the field. With respect to governments, there's a lot of government interest in quantum computing. In large part, actually, because of these kind of cryptographic implications that quantum computers would have. So when Shor's algorithm was first discovered in the mid-1990s, the US realized that quantum computers could actually be used to hack, which of course has big implications for the security of countries and warfare and things like that. So that created a lot of motivation for military investment in the technology, but that's not to say the only application of quantum computers are harmful and scary. That's far from the case. And nowadays, a lot of the government funding is going towards protection from quantum computers and things like that. But just to name a few countries that in particular have invested a lot of money in quantum research, we have France, India, and the US. The US actually, under the recent Trump administration, passed the Quantum Initiative Act, I think is what it was called. Is it? Yeah. The Quantum Initiative Act was $1 billion in funding for quantum computing research. So now is definitely a great time to be in the field. There's a lot of funding for a lot of really cool research, and that's really what's, I think, helping the field progress as rapidly as it is. Amir, do you have anything you wanted to add?
Sorry, actually, as a quick time check, we are running a little bit over. So
Okay.
anything you want to add at the end, that might be best.
Okay, cool. So just to kind of say where we are today, I guess like I've been mentioning, we're still fairly early in the development of quantum computers. In fact, where we are in the state of quantum hardware is probably equivalent to what classical computers were in the 1950s, back when you had the ENIAC computer that took a full room, and really was just kind of like a overly large, somewhat noisy device. And the hope is that we can continue working on quantum computers to progress them to the level that classical computers are today. And they'll give us advantages over the things that classical computers can do today. And of course, it's really important for the future of quantum computing that we have a diverse quantum workforce to really leverage everyone's unique ideas and perspectives in making quantum computers powerful, but also making sure that they're applied to all of the most important settings. And we, yeah, I think just in general, the development of quantum computers will continue to grow much faster if we have people coming in with all different mindsets, perspectives, and ways of problem solving, because it is pretty hard to solve a lot of the problems in quantum computing. There is currently a large quantum talent gap, and by that we mean there's quite a shortage of people who actually know enough about quantum computing to fill all of the interest and positions and kind of research roles that we need in the quantum computing industry and academic setting. So by taking this class, you're really putting yourself in a great spot to join the quantum workforce, which we foresee to grow a lot in the kind of coming years as quantum computers continue to develop and become ever more important in society. And irrespective of whether you see yourself becoming a quantum computing researcher, going into public policy, becoming a climate scientist or a chemist, having knowledge of quantum computing will be super useful. And in fact, even more so, a lot of the fundamentals of quantum computing, ideas from linear algebra, electrical engineering, computer science, will help you in a STEM career in particular, but no matter what you end up doing. So it's really great that you're taking this class as early as you are, and we think it'll help you down the line, irrespective of what job you want. And then Gabby, I don't know if you wanted to conclude by talking about the lab this week.
Yeah, sure. I can touch on this. So as we mentioned before, this week we won't have official lab sections. We will have optional Python review sessions. So if you have never coded before or want a refresher, we'll send out an email tomorrow with the specific details of what we'll cover during these sessions. And so you'll know if you'll want to attend or not. But this will be in place of our lab this week. If you already know Python quite well, you do not need to attend. And then in terms of homework, you will have a pre-course survey to complete that will be sent out on Tuesday as well. Brian, can you go to the next slide? Awesome. And those are the announcements that I just mentioned. Before we sign off, I want to remind everyone that the deadline has been extended, and so we're still accepting applications on a rolling basis until next Saturday. So if you are super pumped by this orientation and you want to share it with a friend, or invite a sibling or cousin to come join us, please do encourage them to apply by that deadline. Although the sooner the better, so that if they are interested, they can get started on these questions as well. Next slide, friend. Perfect. So we have over 1,000 students on the call here. So I just want to remind everyone that you are well on your way to joining nearly 10,000 alumni who've taken this course and gone on and done really remarkable things in a number of areas, not just quantum. And so we're excited that you'll be able to meet fellow alumni at university, at conferences, and even work who knows how far down the line. So we are very, very excited to have all of you all, and we know that we're going to have just a fantastic year and really awesome community that you all have been a part of so far. It's been awesome to see in the chat how everyone has been getting to know each other in the first few minutes of the call, and we're looking forward to continuing that through the year. I'll let Kira add anything if she has any additional comments.
No, I think we're ready to wrap up. Again, really excited to be here on your journey. As Gabby mentioned, since we did get started late for kind of registration, and we know individuals are just starting to find out about this opportunity still, we have extended the deadline since this week is really an orientation. So please share on social media, share with classmates, share with work colleagues. We want to make sure as many people as possible have this opportunity. And with that said, I'm so excited to be along for the ride with all of you. And if we don't see you this week in one of the Python sessions, we will see you next Sunday in our next lecture. Thanks, everyone.